Hello and welcome. Today we are going to talk about Linformer. So the purpose of this video is to actually explain how to apply Linformer the easy way, the easiest way possible, I would say, in PyTorch. And actually it is also a tutorial how to apply Transformer in general in also an easy way. As we can see, there are many resources, many codes, and sometimes things get hard and unnecessarily hard. So Linformer is basically a type of transformer that solves the problem of when we increase the sequence size or the sequence length of the images. As we know, we take the image, we cut it up into, different, depending on our patch size, we cut it up into a sequence, and then we enter that sequence into the transformer model. So when we do that, what happens is as we increase the sequence size, the computation time needed for development and even inferencing is going to be n to the power square. However, if you apply Linformer, the complexity, or not complexity, the computation time will be n to the power n. So how do they do that? The idea is basically when we go to the attention layer, what we have is when we have one sequence and we want to get the attention between these images, these different images, and the other, of course, we have to lie the sequence in one dimension and the other sequence, the same sequence in the other dimension. And then we try to see the relationship between every image and the other image. Well, to do so, usually will require computing n to the power, well, n squared, because we have n and n. So in order not to do that, we need to resize kind of this matrix into a smaller matrix and then do the attention head. So this is the main idea of this Linformer, and we can see, of course, of course, you can read the paper. I will put the description for this video. I will put it in the description of this video, the link of it. And we can see the performance here with a normal transformer when we increase the sequence length. So we have sequence length over patch size. When we increase the sequence length, we will have the inference time increasing. Now I think this one is not maybe it's not like maybe it's different scale, like the not just second, maybe it's log or something different. But the idea is it will keep on increasing, and with Linformer it will stay the same for the time. However, of course, in the beginning of the paper they say the complexity or the computational time will go to the power n here. So, well, this is how this basically the idea of Linformer. Now, the purpose of this video is to explain how to do it, and how to do transformer in general in an easy way. So to do so, what I have seen is I see many resources, but I would say one of the easiest way to do it is described by Mr. Wang here. He just showed a very simple code to apply it, and I'm just explaining it. I'll put all these into the description. And what we can see here, or let's go through the code. And basically what he's doing is first importing libraries. I will explain some interesting things here. Chain, we didn't really use the chain, so I just commented out. Globe is just to see the images in the file, and print function is just it's kind of like changing or printing, or giving some between Python 2 and Python 3, transforming some functionality between both print functionality. And here is normal things: OS, operating system, random, zip file, same things. Matplotlib, NumPy, Pandas, Torch, NN functional if for getting some functions for Torch, and then we have optimization Optim. We have Linformer, and this is important. If you don't have Linformer, you have to pip install it. You can do this command, so you install it, and PIL, of course, you just get the image. We have sklearn, train test split. Step LR is a way to control the learning rate. So we have a little bit dynamic learning rate rather than a fixed value. So we import this library. Data sets, data loader, same thing. We just create data set and we'll create data loader to when we patch our data, transform into patches, and then of course we need to load them into the model. Transformer, well, transformer, this is not the transformer we like. This basically transforming the images to tensors. It's just not the transformer, the visual vision transformer. TQDM, it's just to show the progress bar, and VIT is the vision. VI is vision, T is transformer. So this is the actual library for transformer regarding from PyTorch. So so that's it for the libraries. This is the I ran it on 2.0. I think Mr. Wang ran it different. He ran it on 1.6.0. This is the version of Torch. In my case is 2.0.1. I run it on my local machine. I have one GPU only, so it ran very well. No problems I had. Patch size is 64. You start putting some like hyperparameters, and patch size is 64. Epochs is 20. Learning rate is, you have a value. Gamma is actually related with step learning rate, so it controls the evolution of a learning rate. So this is, you have to give it a value. Seed, you just put it wherever you want, just seed value. First, you seed everything, basically randomize everything. You start by the random function, you seed it, and then OS, the operating system, the PyTorch, you also seed it. NumPy, you give it a random value seed, random value torch. CPU, this one manual seed means like if you're running torch on CPU, it will randomize everything. CUDA for one GPU, it's going to be randomized. CUDA for all CPUs also going to randomize. Torch.backends, I think this one is also randomizing some functionality in PyTorch. But basically this is what he's doing, is just randomizing everything. Device equals CUDA, well, CPU, GPU basically. OS make directory called data, and of course you can do it manually. You don't like, you can do it here or you can do it manually. So basically you have you need to put the training data in here, test data in here. In my case, the train and test data is a zipped file, and then all going to be included in these folders. Well, I can show them the data I have. So basically you have the data here folder, and then you have the test data is going to be cats, like basically cats.1 for number .gpg, and of course dogs also. This is the test. Train is here. You see the data. So just nothing unusual, just same as always. The first thing is you make a training and test list, data list, and you just use glob function. Number of data, training data will be this much, a lot, 23,000 images, about 24,000 images, and test data is only 1,300. It will look like this. Basically, this is the path. So we need to split it, and the way we'll split it is we'll have this like not function outside this syntax. Basically we will split based on these splits. Of course in your computer it might look different. So we have it -1 means he will start from the end of the string, and then he will take this string, this syntax, or this string, sorry, and then he will split it again. This time he will take this part based on this dot. So he will start, he will go from here, and then he will split based on this dot, and then he will take, of course, the cat, or the label, and we have only two, cats or dog. Label is going to be here, and then you have, this is just random plot, so just some random plots. In our case it was cats, but if you run it more, it will start getting some dogs. Here just a train split, usual thing, basically. Train test, train validation between test training and validation, like values, and then you go here and basically just print the number, or the 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 size of the how many images you have. So you have here len of this train test data, some augmentation, and actually transforming the images to tensors. So for the train data, resizing it to 224 and 224, randomize, random size the crop. Basically, he will just crop the image. He will take part of the image, cut it, and then size it to 224. Or make sure that it has 224. Random horizontal flip, you just flip the images randomly, and then you have make it tensor. Transform here for the validation test is first you will upsize the image to have 256, but however it will keep the aspect ratio of the image, so it will have the same aspect ratio, but will be resized to at least 256, one of the dimensions. And then he will go to the center of the image and cut 224 from it. So he will go around the center. 224 by 224 makes it as a square, and then he will make it a tensor, and we'll do the same thing for the testing data. Loading the image, nothing, just same thing. We just add the file data. Transform is this one, we just did it. And len is a little bit strange, but it's len, it just gives you, well, makes you, when you put len the data, you will have the size of the image, or the file length, how many images you have. And here is you get the image. Basically, this is the data set. Just you just take the file the file list, and you start opening the file list. First, you open the image, you transform the image, and then based on the same split I explained before, the syntax that I'm going to split the label and the data, you will give it a number. If it's dog, let's say 1, and if it's cat, it will be 0, and according to this, and then you return back the image and the label. You will call this function dataset, and then you will train data, valid data, test data. You'll do the same thing, just put the data inside. Data loader. Now, once you have the data set, you need to well, cut them into patches. So you will do that with this data loader. Dataset is this one, patch size is patch sizes, shuffle if it's true. Well, basically you want to shuffle the images, and then just like continue, and you have the length of the train loader. Basically this one will have a different length, of course, because we know the patch size that we have, I think, is 64. And then you will have this 64 images as one patch, and then it will have to cut your 18,000 or about 19,000 and put it into 64 images. So you will have this number of like patches, and then of a patch size of 64 images. You do the same for valid, just this is why the numbers here exist. Now after that, you will define the transformer, and you Linformer. You start with Linformer. The the first dimension is actually the embedding dimension here. So you have the embedding dimension of 128. That means every small patch of images will be embedded into 128 values, or 100 the patch the embedding dimension. Sequence length is 49 plus 1. This is the allowable sequence for this transformer to be 49 sequences, and 1 is the CLS token, which is the token that represents the whole image. So this is the length of it for this transformer, and then depth is 12. Depth means the number of layers of transformer that you will add these like the images to it, and of course after that it will be concatenated. You can see that in the paper actually. You can see here all these layers will be these are the layers we're talking about, and then will be concatenated at the end, and then you will have feed forward network. Here you have a depth of 12, so 12 layers, heads of 8, and heads is the number of ways you are representing the relationships, the attentions between the parts of image with respect with the other parts of the image. So here you have 8. K equals 64 is the number we talked about that is related to resizing this. You have the sequence length will change, and then you want to resize it to a specific number. This K is going to be that number. The bigger it is, the computation will increase according to this paper. So you can say K 128 is this one, and then you have as the bigger it is, it will consume more time. And here you have the model visual transformer. Models dimension, again the embedding dimension should be the same as before. Image size 242. Patch size is 32, and 32 means basically you will cut the image into 32 patches. In this case, when you divide 224 on 32, you will get 7 by 7 like pixel. Here the patch size. Number of classes is 2, of course, cats and dogs. Efficient transformer is you just what kind of transformer you want to use, which is here efficient transformer, and the number of channels is 3, red, blue, green. You start the training same as usual. You criterion the cross entropy function loss. Optimizer is Adam. You have a scheduler. This is a little bit not always done. Gamma is going to change the learning rate. So you take this optimizer, you feed it here, and then it will change its learning rate. And after that, you just do the training. So you have the epochs, and it will run. You keep training, and then epoch loss, accuracy loss is going to be starting 0, and then you will do the training here. And the training is basically you upload the data, the data to the device, the labels you uploaded against to the device. Output, you will calculate the output from this data using the model we have, which is the transformer. You calculate the loss by comparing the output with the labels, and then you zero the grade, you make back propagation, and then you optimize based on the back propagation you have. And then you will calculate the accuracy, epoch accuracy, epoch loss from all of this. Of course, this is you just calculate the accuracy based on this number, and then you divide by the number of the the data loader. And then what you will do is you will do the same thing for validation. You do the validation data, same thing, data, labels, and then you will predict the output for this data, the validation data, and then you calculate the loss, and then of course you don't update the weights because it's only validation, and then you calculate the accuracy, you print everything, and then you will get this thing. That's it. We're done. But just a little bit, we keep doing this. 20. At the end, the accuracy was 70%. Yeah, not so good, but it's very typical for just beginning, like just try something to put it together. Inputs and labels, test loader. This is, I just added this. It's not included in Wang's like a code, which is basically just take the data, the test data, and upload it, and then get the outputs and see how many of the compare the predicted output with the actual output, and we can see here the result. So here is the predicted result, and of course it's not 100% matching the the actual result. Of course, you want to, in order to apply this into a real problem, what you need to do is you just need to try to change the hyperparameters, try to change the data, try to see the ratio between the data. It seems more cats that we have more than dogs. We have to see how many dogs is it sufficient. And yeah, and of course augmenting the data if you needed. So you do this until you get a better result and better accuracy. So that's it for today, and it is and hopefully you understood now how to apply the transformer in an easy way, and also learn more about the the new type of transformer that we had, the Linformer, this one. So hopefully it was enjoyable, and let's see you next time.